Right now, beneath the border of Switzerland and France, physicists are measuring something that does not quite add up. In collisions that recreate conditions hotter than the core of the sun by a factor of 100,000, energy goes missing, not lost to errors, not explained by known particles, just gone. And when energy vanishes from a closed system, it suggests something invisible carried it away. By the end of this breakdown, you will understand what experiment could lead people to say a crack in reality, what scientists actually measured, and how to tell the difference between observation and speculation. If this is the kind of science you like, subscribe for more breakdowns like this. Let's break it down, step by step. The phrase crack in reality appeared in headlines following reports from the Large Hadron Collider experiments. The claim suggests a boundary has been breached, that particles are escaping into dimensions we cannot see, or that fundamental forces are behaving differently than predicted. But what would have to be true if reality had developed a crack? First, conservation laws we have tested for over a century would need to fail. Energy or momentum would have to vanish without a contact. Second, particles would need to interact with something beyond the standard models known forces in matter. Third, the effect would need to be reproducible, consistent, and statistically significant beyond detector uncertainties. Those are stringent conditions. CERN's detectors measure millions of collisions every second. They track particle paths with precision down to micrometers. They calculate momentum and energy balance across hundreds of detector layers. If something truly anomalous is happening, the data must show it clearly and repeatedly. So what did they actually measure? CERN is the European Organization for Nuclear Research, located near Geneva. The Large Hadron Collider is a circular accelerator 27 kilometers in circumference. It accelerates protons to 99.999991% the speed of light, then collides them at 4 interaction points. Each collision point houses a detector. ATLAS and CMS are general-purpose detectors. LHCb studies particles containing bottom quarks. ALICE focuses on heavy ion collisions. The LHC does not open portals. It does not drill into other dimensions. It collides particles. When two protons collide at 13.6 trillion electron volts, their kinetic energy converts into mass according to Einstein's relation. New particles emerge. Quarks, gluons, bosons. These particles decay almost instantly into lighter particles, which decay again, until only stable particles like electrons and photons remain. Detectors record the traces. Computers reconstruct what happened. Look at this. A single collision might produce 50 particles. Each leaves a signature. Charged particles curve in magnetic fields. Photons hit calorimeters and deposit energy. Muons penetrate multiple detector layers. The pattern tells the story. Collision energy versus everyday intuition requires clarification. 13.6 trillion electron volts sounds immense. In everyday units, it equals roughly the kinetic energy of a flying mosquito. The difference is concentration. That energy is compressed into a space smaller than a proton. This energy density is what recreates early universe conditions, not the total energy. A cosmic ray hitting Earth's atmosphere can carry 1,000,000 times more energy than an LHC collision. Nature performs these experiments constantly. Notice what changes when energy increases. At lower energies, collisions produce mostly light particles, pions, kaons. At higher energies, heavier particles emerge. W bosons, Z bosons, top quarks. The Higgs boson requires about 125 billion electron volts to materialize. Physicists discovered it in 2012 by colliding protons at 7 trillion electron volts and seeing occasional Higgs production. The LHC cannot create anything that cosmic rays have not already created billions of times. Particles from deep space strike Earth's atmosphere with energies up to 100 million trillion electron volts. Those collisions happen continuously and have for billions of years. If cosmic ray collisions could produce dangerous stable objects, we would see evidence in astronomical observations. We do not. Neutron stars, white dwarfs, the moon, Earth itself remains stable. This constrains what the LHC could possibly produce. Keep that in mind. The cosmic ray analogy is not a hand wave. It is quantitative. Over the past 4.5 billion years, Earth has experienced more collisions at LHC energies than 30 million LHC experiments running for their full operational lifetime. The universe performs more than 10 million LHC equivalent collisions every second. If a process could destroy matter or create runaway reactions, it would have happened. Stars would vanish, galaxies would collapse. They do not. So, if the LHC cannot do anything nature has not done, where does the crack in reality claim come from? Candidate 1 for the crack in reality narrative involves missing energy. In particle physics, missing energy means the total momentum before and after a collision does not balance. This happens when particles escape the detector without interacting. Neutrinos are the most common cause. They interact only through the weak force and gravity. Most pass through the entire detector without leaving a trace. Physicists infer their presence by measuring everything else and calculating what is missing. Here's the key detail. Momentum conservation is absolute in isolated systems. When two protons collide, the total momentum after the collision must equal the total momentum before. If detectors measure all outgoing particles and find an imbalance, something invisible carried away the difference. This method has been used for decades to discover neutrinos, and now to search for new physics. Imagine a pool table. You know the cue ball's speed and direction. It strikes another ball. Both balls scatter. If you measure their final velocities and directions, you can verify momentum conservation. If the total momentum after does not match the total before, either your measurements have errors, or a third ball you did not see carried away the difference. LHC detectors work similarly but in 3 dimensions with magnetic fields. Charged particles curve. The radius of curvature reveals their momentum. Neutral particles hit calorimeters and deposit energy proportional to their mass and speed. Muons penetrate to outer detector layers. By combining all signals, physicists reconstruct the event. If the sum does not balance, they report missing transverse energy. Now zoom out. Missing energy searches at the LHC focus on events with large momentum imbalances. A typical search looks for a high-energy jet plus missing energy, or a photon plus missing energy. These signatures appear when a dark matter particle pair is produced. One hypothesis is that dark matter particles are weakly interacting massive particles, or WIMPs. If WIMPs exist and can be produced at LHC energies, they would escape the detector, creating a momentum imbalance. The ATLAS and CMS experiments have conducted numerous searches. They set limits on how often missing energy events occur. These limits constrain theoretical models. For example, if a model predicts 1,000 dark matter production events per year and the experiment sees none, the model is excluded or must be revised. These constraints are published as exclusion plots showing which parameter space is ruled out. But here is the critical distinction. Absence of evidence is not evidence of absence. Not finding dark matter at current energies means either it does not exist, or it is heavier than the LHC can produce, or it interacts too weakly to be detected. Physicists separate observation from interpretation. Observation: no significant excess of missing energy events beyond standard model predictions. Interpretation: this constrains but does not rule out dark matter models. Non-exotic causes of missing energy must be addressed first. Detector inefficiencies: particles hitting dead regions, mismeasured jet energies, neutrinos from heavy quark decays, cosmic rays coinciding with collisions. These backgrounds are estimated using control regions, data-driven methods, and simulations. Only after accounting for known sources can physicists claim an anomaly. What new physics searches would look like involves defining a signal region and background estimation. Signal region: events with specific characteristics, like one high-energy jet and missing energy above a threshold. Background estimation: using events that pass most cuts but fail one, or using Monte Carlo simulations validated with data. If observed events significantly exceed background predictions, that is an anomaly. If they match predictions, there is no signal. The LHC has delivered over 500 inverse femtobarns of integrated luminosity to ATLAS and CMS. One inverse femtobarn corresponds to about 100 trillion collisions. With that much data, rare processes become visible, but the standard model predicts backgrounds accurately. Most missing energy events are from neutrinos in W or Z boson decays or top quark decays. These are well understood. What this implies is that the crack in reality, if interpreted as missing energy, is not a crack at all. It is a search for new physics using a well-established technique. The absence of a discovery so far tightens constraints on dark matter and other beyond standard model phenomena. This is progress, not panic. So, if missing energy is not the crack, what other anomaly could fuel the claim? Candidate 2 for crack in reality claims involves anomaly signals in particle decay patterns. An anomaly in this context means a statistically significant deviation from standard model predictions. Many anomalies have appeared in LHC data over the years. Most fade as more data accumulates. A few persist and require explanation. Define anomaly precisely. Physicists measure a quantity, like the rate at which a B meson decays to muons versus electrons. The standard model predicts these rates should be nearly identical due to lepton flavor universality. This principle states that electrons, muons, and taus couple with equal strength to the weak force, differing only by mass. If measurements show a consistent deviation, that is an anomaly. The LHCb experiment reported such deviations in rare B meson decays starting in 2014. Measurements of the ratio of decays to muons versus electrons were lower than standard model predictions by about 2 to 3 standard deviations. This persisted across multiple decay channels. The physics community took notice. Could this be the first evidence of physics beyond the standard model? New particles coupling differently to different lepton generations? Notice what changes with more data. Early measurements had large uncertainties. A 2 standard deviation difference is interesting but not conclusive. Particle physics uses a 5 standard deviation threshold for claiming a discovery. That corresponds to a probability of less than 1 in 3.5 million that the result is a statistical fluctuation. Below 5 sigma, results are considered hints, not discoveries. LHCb continued collecting data. In 2025, they presented updated results using the full dataset from Run 1 and Run 2. The improved analysis employed more robust techniques and reduced systematic uncertainties. The result? The anomaly disappeared. The new measurements are consistent with standard model predictions within uncertainties. Lepton flavor universality holds. This is how science works. Initial tensions drive theoretical speculation and experimental scrutiny. Further data either confirms the anomaly, elevating it to a discovery, or resolves it, confirming the standard model. Both outcomes advance knowledge. In this case, the resolution validates the standard model's predictions once more and demonstrates the importance of statistical rigor. Here's why many anomalies fade with more data. Small data sets have large statistical fluctuations. An early measurement might fluctuate upward or downward by chance. As more data accumulates, the true value emerges. Additionally, systematic uncertainties decrease with better understanding of detector performance, backgrounds, and analysis techniques. What appeared anomalous with preliminary data often aligns with predictions when fully analyzed. Replication is essential. An anomaly reported by one experiment must be confirmed by another. If Atlas sees an excess at a certain mass, CMS must see it too. If only one experiment reports it, it could be a detector artifact or analysis error. Cross-checks between experiments provide confidence. In the case of the LHCb lepton universality measurements, the updated results used improved methods and were scrutinized extensively before publication. Uncertainties in systematics require careful treatment. Every measurement has statistical uncertainty, which decreases with more data, and systematic uncertainty, which depends on how well the detector and analysis are understood. Systematic uncertainties can include trigger efficiencies, particle identification, background modeling, and luminosity calibration. Physicists spend considerable effort validating these systematics using control samples. What this implies for crack in reality narratives is clear. Anomalies that initially appear significant often resolve with further investigation. The process is iterative. Report attention. Theorists propose explanations. Experimentalists refine measurements. Either a discovery emerges or the standard model is reaffirmed. The lepton flavor universality case exemplifies this. A sustained anomaly would have been groundbreaking, but its resolution strengthens confidence in our understanding. If not missing energy and not resolved anomalies, what remains? The panic myth section addresses the fears that generate sensational headlines. Three scenarios dominate public anxiety: micro black holes, strangelets, and vacuum decay. Each requires scientific explanation, not dismissal. Micro black holes: why people fear it. The term black hole evokes images of cosmic devourers, regions of space where gravity is so strong that nothing, not even light, escapes. Stellar mass black holes form from collapsing stars. Supermassive black holes anchor galaxy centers. But what about microscopic black holes? Some theoretical models predict that if extra-spatial dimensions exist, gravity could become strong at small scales, allowing micro-black holes to form in high-energy collisions. The fear is straightforward. A micro-black hole produced at the LHC might not evaporate. It could accrete matter, growing larger, eventually consuming Earth. This scenario appeared in media coverage and even lawsuits attempting to halt LHC operations. Understanding why this is not a concern requires examining the physics. According to general relativity as formulated by Einstein, it is impossible for microscopic black holes to be produced at the LHC. Gravity is far too weak at these scales. However, speculative theories involving extra dimensions suggest otherwise. If such theories are correct, micro black holes could be produced, but all these theories predict immediate evaporation via Hawking radiation. Hawking radiation is a quantum effect where black holes emit particles and lose mass. The smaller the black hole, the faster it evaporates. A micro black hole with the mass of a few protons would decay in about 10 to the minus 27 seconds. That is an unimaginably short time. The black hole would disintegrate into standard model particles before reaching the detector walls. Experiments would see an exceptional number of particle tracks, a clear signature but no lasting black hole. Even if Hawking radiation were somehow wrong and micro black holes were stable, cosmic rays provide a safety argument. Cosmic rays with energies far exceeding the LHC strike Earth, the Moon, the Sun, neutron stars, and white dwarfs constantly. If stable micro black holes could be produced and were dangerous, astronomical bodies would show effects. Neutron stars are incredibly dense. A micro black hole accreting matter inside a neutron star would alter its structure detectably. Observations show no such anomalies. Neutron stars exist as predicted. This constrains the danger from any hypothetical stable micro black holes to negligible levels. The LHC Safety Assessment Group, composed of independent physicists, reviewed these scenarios extensively in 2003 and 2008. Their reports concluded that LHC collisions present no danger. The arguments are quantitative. Over the age of the Earth, cosmic rays have delivered more than 30 quadrillion collisions at energies equal to or greater than the LHC. If any process could create a dangerous object, it would have occurred. Earth still exists. The argument is airtight. Strangelets. What it is. A strangelet is a hypothetical form of matter composed of up, down, and strange quarks in roughly equal numbers. Ordinary matter contains only up and down quarks. Strange quarks are heavier and appear in particles like kaons and lambda baryons, which decay quickly. But some theories speculate that a stable configuration of strange matter could exist, potentially at lower energy than ordinary matter. The fear is that if a strangelet formed, it could convert ordinary matter into strange matter upon contact. This chain reaction would spread, converting Earth into a dense lump of strange quark matter. This scenario is sometimes called an Ice 9 scenario, referencing a fictional substance from Kurt Vonnegut's novel that crystallizes all water it touches. Why it is considered extremely unlikely requires understanding production mechanisms and stability. Strangelets would require high baryon density and low temperature to be stable. LHC collisions, even heavy ion collisions, create extremely high temperatures. At 13.6 trillion electron volts for proton collisions or 5.02 trillion electron volts per nucleon pair for lead ion collisions, the environment is far too hot for strange matter condensation. It is thermodynamically analogous to trying to form an ice cube in a furnace. Experimental evidence from the relativistic heavy ion collider further constrains strangelet production. RHIC collided gold nuclei at lower energies than the LHC, creating conditions that were arguably more favorable for strangelet formation. No strangelets were observed. The LHC's higher energies make production even less likely. Additionally, the LHC Safety Assessment Group's analysis showed that even if strangelets formed, they would be positively charged and repelled by ordinary matter, preventing runaway conversion. Cosmic ray collisions again provide a benchmark. High-energy cosmic rays collide with the Moon's surface, which consists of ordinary matter in a center of mass frame similar to LHC heavy ion collisions. The Moon has been bombarded for billions of years. If strangelets could form and convert matter, the Moon would show signs. It does not. This observation rules out dangerous strangelet production at LHC energies, vacuum decay, or false vacuum. Explain the idea carefully. The concept of a false vacuum comes from quantum field theory. The Standard Model's Higgs field has a potential energy that determines its stability. If the universe's vacuum state is not the lowest possible energy state, it is a false vacuum. A quantum fluctuation could trigger a transition to a true vacuum, forming a bubble that expands at the speed of light, destroying everything in its path. Some calculations suggest that the measured Higgs boson mass, 125 billion electron volts, places the universe in a metastable state, not immediately unstable, but vulnerable to tunneling into a lower energy state over extremely long timescales. The concern is whether LHC collisions could trigger such a transition. Why collider energies are not comparable to cosmic scales is crucial. The energy density in a proton-proton collision is high, but it occupies an infinitesimal volume for an infinitesimal time. Vacuum decay calculations depend on energy density sustained over macroscopic regions and timescales. LHC collisions last about 10 to the minus 23 seconds and occur in a region smaller than a proton. Cosmic rays achieve much higher energies and have been occurring throughout the universe for billions of years. If vacuum decay could be triggered by particle collisions, it would have happened from cosmic rays. The observable universe shows no evidence of vacuum decay bubbles. The LHC Safety Assessment Group addressed this explicitly. They noted that if the vacuum is metastable, the timescale for spontaneous decay is vastly longer than the age of the universe. Particle collisions, whether from accelerators or cosmic rays, do not provide sufficient conditions to catalyze the transition. The energy density and duration are orders of magnitude below the threshold. What this means for the crack in reality narrative is that the panic myths are based on misunderstanding the physics. Micro-black holes evaporate instantly or are constrained by cosmic ray observations. Strangelets are thermodynamically disfavored at LHC temperatures and excluded by experimental limits. Vacuum decay requires conditions far beyond what colliders provide. These are not cracks in reality. They are speculative scenarios thoroughly investigated and ruled out. So, how did these myths spread? How the panic is manufactured involves tracing the distortion chain from scientific results to sensational headlines. The process begins with a preliminary result. Researchers at Atlas or CMS observe an interesting feature in data. They prepare a conference presentation or submit a preprint to the ARXI. At this stage, the result is tentative. Statistical significance might be low. Systematic uncertainties are still being evaluated. The paper or talk is accurate. It describes the measurement, uncertainties, possible interpretations. It uses cautious language, suggests, consistent with, constrains. The conclusion states that more data is needed to confirm or refute the observation. This is responsible scientific communication. Then the press office writes a press release. Press releases aim to make research accessible to non-specialists. They simplify technical details. They emphasize the novelty. Sometimes they include quotes from scientists explaining why the research is interesting. But simplification can introduce ambiguity. A phrase like could hint at new physics becomes could reveal new physics in a headline. Now zoom out. Journalists receive the press release. Science journalists familiar with particle physics might read the actual paper and interview the researchers. They write balanced articles explaining the result, its significance, and limitations. But not all journalists have that expertise or time. Some rely on the press release alone. Others prioritize clicks. A headline that reads, "CERN experiment hints at physics beyond standard model" is informative. A headline that reads, "CERN discovers crack in reality" generates more engagement. Social media amplifies the distortion. A well-written article might have a measured headline, but the tweet sharing it uses sensational phrasing. Readers scroll past without clicking. They absorb the headline. They share it. Each iteration moves further from the source. By the time the story reaches YouTube or forums, it is unrecognizable. The original preliminary 2 sigma hint becomes definitive proof of alternate dimensions. Teaching the viewer to spot inflated language is essential. Absolutist wording is a red flag. Words like proves, confirms, shatters, breaks, revolutionizes should trigger skepticism unless backed by 5 sigma evidence and replication. Science rarely proves anything definitively. It constrains, refines, suggests. A legitimate discovery uses phrases like observes with high significance, consistent with the hypothesis, supports the model. Look at this example. An atlas result states, "We measure the production cross-section of W boson pairs and find consistency with standard model predictions within uncertainties, though a slight excess at high mass is observed with 2.1 sigma significance." This is careful and honest. A sensational headline might read, "CERN detects anomalous signal that could rewrite physics." The headline is not entirely false, but it misleads by omission. Compare 2 framings of the LHCb lepton universality results. Accurate framing. Updated measurements of rare B meson decays show agreement with lepton flavor universality predictions, resolving earlier tensions. Sensational framing. CERN experiment confirms. Fundamental force behaves unexpectedly, then mysteriously returns to normal. The second framing implies conspiracy or instability rather than the normal scientific process. Another tactic is the appeal to authority without context. A headline might cite a scientist saying, "This could be the most important discovery in decades." The quote is real, but it was about a hypothetical scenario, not the actual result. Or the scientist was discussing what a 5 sigma discovery would mean, not a 2 sigma hint. Context matters. What this implies for evaluating crack and reality claims is clear. Trace the claim back to the source. Is there a published paper? What collaboration reported it? What is the statistical significance? Have other experiments confirmed it? If the only source is a headline or social media post, it is likely distorted. Legitimate results appear in peer-reviewed journals or official collaboration reports. So how can you verify claims yourself? Viewer Toolkit. How to verify crack in reality. Claims begins with recognizing red flags and green flags. Red flags indicate a claim is likely exaggerated or false. Green flags suggest credibility. Applying this checklist helps navigate sensational science coverage. Red flags include absence of a named detector or collaboration. If a headline claims CERN made a discovery but does not specify Atlas, CMS, LHCb, or ALICE, be skeptical. Legitimate results come from specific experiments. Another red flag is no paper or preprint linked. Claims without references to arXiv, physical review letters, Nature, or CERN official reports are suspect. If the source is a YouTube channel or blog with no citations, disregard it. Absolutist wording is a red flag. Phrases like proves, breaks all known physics, confirms other dimensions should raise alarms. Physics progresses incrementally. Even major discoveries use restrained language in official publications. The Higgs boson discovery paper states, "A particle with properties consistent with the standard model Higgs boson has been observed." Not proves Higgs exists. Claims of suppression or conspiracy are red flags. If the claim includes scientists are hiding this or mainstream physics refuses to acknowledge, it is almost certainly false. The scientific community thrives on challenging existing models. A genuine anomaly would be investigated intensely, not suppressed. Green flags include a named collaboration and official source. If the claim references Atlas collaboration published in Physical Review D, that is verifiable. Go to the journal or arXiv and read the abstract. Another green flag is cautious verbs. Suggests, indicates, constrains, is consistent with, raises questions. These signal careful scientific communication. Inclusion of statistical significance and uncertainties is a green flag. A result stating 3.5 sigma with systematic uncertainties of 5% shows rigor. Acknowledgement of what is not known is also positive. Statements like further data is needed or alternative explanations cannot be ruled out indicate honesty. Replication by independent experiments is crucial. If Atlas reports an excess and CMS confirms it, credibility increases. If only one experiment reports it and others see nothing, wait for more data. Cross-experiment consistency is a strong green flag. What would count as a true breakthrough involves specific criteria. First, statistical significance must reach or exceed 5 sigma. This corresponds to a probability of less than 1 in 3.5 million that the result is a fluctuation. Second, replication by at least one independent experiment is required. Third, the result must be published in a peer-reviewed journal after scrutiny by experts. Fourth, the signal must persist with more data, not fade. Examples of true breakthroughs include the Higgs boson discovery in 2012, the observation of gravitational waves in 2015, and the detection of neutrino oscillations in the late 1990s. Each met the criteria. Multiple experiments confirmed the results. Statistical significance was overwhelming. Theoretical predictions aligned with observations. For a crack in reality to be real, it would need to show a reproducible violation of conservation laws or detection of particles interacting outside the standard model with 5 sigma significance and independent confirmation. It would need to survive scrutiny, peer review, and accumulation of additional data. No such result currently exists from the LHC. Apply the checklist to a hypothetical claim. Headline: CERN detects portal to another dimension. Red flags: no named experiment, no paper, absolutist wording. Conclusion: almost certainly false. Revised headline based on actual research. Atlas searches for dark photons in rare decays, sets new limits. Green flags: named experiment, cautious language, implies a search rather than a detection. Conclusion: credible, though not a discovery. The checklist is not foolproof, but it filters out most nonsense. When in doubt, go to CERN's official website, search for press releases, or check the collaboration's publication list. Peer-reviewed results are the gold standard. Everything else is speculation. So, what is the real crack? Ending. The real crack is the boundary of our models. The standard model describes particle physics with extraordinary precision. It predicted the Higgs boson, W and Z bosons, top quark, and countless decay processes, all confirmed experimentally. Yet, the standard model is incomplete. It does not explain dark matter, which constitutes 85% of the universe's matter. It does not explain dark energy, which drives accelerated expansion. It does not incorporate gravity at quantum scales. It does not explain why matter dominates over antimatter. These gaps are not flaws. They are signposts. The standard model is a phenomenally successful, effective theory, valid up to certain energy scales and conditions. Beyond those boundaries, new physics must emerge. The LHC probes those boundaries. Each collision tests whether the standard model holds or breaks. So far, it holds. The real crack in reality is not a tear in space-time or a gateway to other dimensions. It is the edge of our knowledge. Every measurement that matches standard model predictions narrows the space where new physics could hide. Every search that finds nothing rules out models and tightens constraints. This is progress. It tells us where not to look and sharpens the questions for the next generation of experiments. Consider what the LHC has achieved. It discovered the Higgs boson, completing the standard model's particle roster. It measured the Higgs properties with increasing precision, confirming its role in electroweak symmetry breaking. It constrained supersymmetry, extra dimensions, and dark matter models. It studied quark-gluon plasma, the state of matter a microsecond after the Big Bang. It tested lepton flavor universality and confirmed quantum chromodynamics predictions. These accomplishments advance fundamental understanding. They do not make headlines about cracks in reality, but they represent humanity's deepest probes into nature's laws. The LHC is scheduled to run through the late 2030s. After that, Proposals exist for a future circular collider with a circumference of 100 kilometers and collision energies up to 100 trillion electron volts. That next machine might finally access the energy scales where dark matter particles could be produced, or where the Higgs field's properties reveal hints of new symmetries. The final forward pull question is this: what measurement would settle the biggest uncertainty next? For dark matter, direct detection experiments and LHC searches together could corner the parameter space. If WIMPs exist below a certain mass, LHC searches would have found them. If they exist above a certain cross-section, direct detectors would have seen them. The combination constrains or discovers. For the Higgs mechanism, precise measurements of Higgs self-coupling could reveal whether the Higgs potential has unexpected features hinting at new physics. For the nature of neutrinos, determining whether they are Majorana or Dirac particles and measuring the absolute mass scale would answer fundamental questions. For matter-antimatter asymmetry, studying CP violation in rare decays could identify new sources of symmetry breaking. Each of these fronts requires different experiments, different techniques, converging toward a unified picture. The crack in reality narrative misses the point. Science is not about dramatic revelations. It is about incremental refinement, rigorous testing, and honest acknowledgement of uncertainty. The LHC's legacy will not be a crack in reality. It will be the thousands of measurements that define the boundary between what we know and what remains to be discovered. That boundary is where the next generation of physicists will work. That boundary is the real frontier. And that is the story behind the panic. Not a crack, but a search. Not fear, but curiosity. Not the end of physics, but the beginning of the next chapter. The detectors themselves warrant deeper examination. Atlas is 46 meters long and 25 meters high. It weighs 7,000 tons. CMS is 21 meters long, 15 meters in diameter, and weighs 14,000 tons. These are not simple cameras. They are layered instruments, each layer designed to measure different particle properties. Start from the collision point and move outward. Closest to the beam pipe is the inner tracking detector. This consists of silicon pixel and strip detectors that record charged particle paths with micrometer precision. When a charged particle passes through silicon, it ionizes atoms, creating a signal. By measuring where particles hit across multiple layers, the detector reconstructs their trajectories. Next comes the electromagnetic calorimeter. This measures the energy of electrons and photons. These particles create showers of secondary particles in dense material. The shower deposits energy, which is measured. Photons have no charge, so they leave no track in the inner detector. Their first signature is in the calorimeter. Electrons leave both a track and a calorimeter deposit. Beyond that is the hadronic calorimeter. This measures the energy of hadrons, particles made of quarks, protons, neutrons, pions, kaons. These interact via the strong force and create hadronic showers. The calorimeter absorbs the shower and measures the energy. Together, the electromagnetic and hadronic calorimeters capture most particles. Finally, the muon system. Muons are heavy versions of electrons. They penetrate through calorimeters with minimal energy loss. The outermost detector layers specifically track muons. Large chambers filled with gas detect muon paths. Muons are important because they appear in many interesting processes, including Higgs decays and searches for new particles. The magnetic field is crucial. Atlas and CMS use superconducting magnets to create fields of 2 to 4 Tesla. For comparison, a refrigerator magnet is about 0.01 Tesla. The strong field bends charged particle paths. The more momentum a particle has, the less it bends. By measuring the curvature, physicists calculate the momentum. The sign of the curvature reveals the charge. Positive particles curve one way, negative, the opposite. Data acquisition happens at staggering rates. Protons collide 40 million times per second. Each collision might produce hundreds of particles. Recording every collision would generate petabytes per second. Storage and analysis are impossible at that scale. Instead, a trigger system selects interesting events in real time. The trigger looks for patterns. High energy particles, missing energy, multiple leptons. Events passing the trigger are saved. The rest are discarded. This reduces the data rate to about 1,000 events per second. Processing those events requires massive computing. The worldwide LHC computing grid distributes data to hundreds of institutions. Physicists write algorithms to reconstruct particles from raw detector signals, identify particle types, and search for specific processes. A single physics analysis might take months and involve dozens of researchers. Understanding collision energy in practical terms helps. 13.6 trillion electron volts per collision, or 6.8 trillion electron volts per proton, compresses enormous energy into tiny space. In macroscopic terms, the energy of one LHC proton beam equals the kinetic energy of an aircraft carrier moving at over 20 kilometers per hour. But that energy is distributed among 100 billion protons in bunches just micrometers wide. Each bunch collision involves only a tiny fraction of protons. Most protons pass through each other without interacting. When protons do collide, they do not collide as holes. Protons contain quarks and gluons, collectively called partons. At high energies, a collision is between individual partons. A quark from one proton might strike a gluon from another. The collision produces a shower of particles. Quarks and gluons cannot exist in isolation. They immediately form bound states, mesons and baryons. This process is called hadronization. The resulting spray of particles is called a jet. Jets are the most common signature at the LHC. Physicists study jet properties, energies, and multiplicities to test quantum chromodynamics, the theory of the strong force. Deviations from QCD predictions could signal new physics. So far, QCD holds. Jets behave as predicted across a vast energy range. What the LHC cannot do is as important as what it can. It cannot open portals to other dimensions in any science fiction sense. Dimensions in physics are mathematical constructs. If extraspatial dimensions exist, they are compactified, curled up at scales far too small to traverse. Particles might propagate into these dimensions briefly, which would manifest as missing energy. But there is no gateway, no tear in space-time. It cannot create stable, dangerous black holes. Even if micro-black holes form, they evaporate nearly instantaneously. The physics is well understood. Hawking radiation ensures that small black holes decay faster than large ones. A black hole with the mass of a proton evaporates in less than 10 to the minus 27 seconds. It decays into ordinary particles before traveling a distance smaller than a proton's diameter. It cannot trigger vacuum decay. The energy density and duration of collisions are insufficient. Cosmic rays with higher energies have bombarded Earth and astronomical bodies for billions of years. No vacuum decay events have occurred. The LHC operates well within the safe parameter space established by nature's own experiments. So if the LHC is just a very precise collision recorder, where does the crack in reality narrative originate? It comes from misunderstanding what missing energy signifies. Missing energy is not mysterious. It is an inference. When physicists balance momentum before and after a collision and find a shortfall, they infer that invisible particles carried away the difference. This technique discovered the neutrino in the 1930s. Wolfgang Pauli proposed the neutrino to explain missing energy in beta decay. Enrico Fermi developed the theory. Decades later, neutrinos were directly detected. Missing energy went from mystery to established physics. Dark matter searches use the same logic. If dark matter particles are produced in LHC collisions, they would escape detection, creating missing energy. Searches look for events where all visible particles account for only part of the initial momentum. The remainder is attributed to invisible particles. If the rate of such events exceeds standard model predictions, it could indicate dark matter production. Experiments report results as exclusion limits. These are plotted as graphs showing the parameter space ruled out. For example, a plot might show dark matter mass on the x-axis and interaction cross-section on the y-axis. The shaded region is excluded by experimental data. Models predicting parameters in that region are inconsistent with observations. The unshaded region remains allowed. These plots are refined with each data update. As more collisions are analyzed, the excluded region grows. This constrains theoretical models. If a model predicts dark matter with a mass of 100 billion electron volts and a certain interaction strength, and the LHC excludes that combination, the model must be revised or discarded. This is how science progresses. Theories make predictions. Experiments test them. Theories that fail are abandoned. Theories that survive are refined. Atlas and CMS have published numerous missing energy searches. They look for dark matter produced in association with jets, photons, W bosons, Z bosons, Higgs bosons. Each channel provides different sensitivity. Combined, they cover a wide range of dark matter models. The results? No significant excess. The data matches standard model predictions. This means either dark matter is heavier than the LHC can produce, or it interacts too weakly to be detected, or it does not couple to standard model particles in the ways tested. This non-discovery is valuable. It tightens constraints. Before the LHC, the possible parameter space for dark matter was vast. Now, large regions are excluded. Future experiments, like direct detection experiments deep underground or indirect detection via cosmic rays, can focus on the remaining allowed regions. The LHC and these other experiments work together, triangulating the properties of dark matter from different angles. Neutrinos are a known source of missing energy. W bosons decay to a lepton and a neutrino. Z bosons can decay to neutrino pairs. Top quarks decay to W bosons, which decay to neutrinos. These processes are common at the LHC and are precisely predicted by the standard model. Background estimation accounts for them. Physicists use control regions where neutrino processes dominate to validate their background models. Only after confirming that backgrounds are well understood do they interpret excesses as potential new physics. Detector inefficiencies also contribute to apparent missing energy. If a particle enters a dead region of the detector or is mismeasured, momentum balance appears off. These effects are studied using test beams, cosmic ray data, and careful detector calibration. Systematic uncertainties from detector performance are included in all analyses. The point is that missing energy is not a crack. It is a signature. Physicists search for anomalies in that signature, comparing observed rates to standard model predictions. When observations match predictions, the standard model is validated. When they do not, further investigation determines whether the excess is statistical fluctuation, systematic error, or genuine new physics. The process is rigorous. Claims of discovery require overwhelming evidence. What distinguishes a real anomaly from statistical noise involves significance and reproducibility. A 1 sigma fluctuation is expected about 1/3 of the time. A 2 sigma fluctuation occurs about 5% of the time. Neither is compelling evidence. 3 sigma is considered evidence, but not discovery. 5 sigma is the threshold for claiming a discovery in particle physics. This corresponds to a 1 in 3.5 million chance of being a random fluctuation. Why such stringent requirements? Because particle physics involves millions of measurements. If you measure 1,000 quantities and use a 95% confidence level, you expect 50 false positives by chance. Without a high threshold, spurious signals would dominate. The 5 sigma standard ensures that discoveries are robust. Reproducibility is equally critical. If Atlas sees an excess, does CMS see it? If the LHC sees it, do Fermilab or other facilities see it? If a signal appears in 1 year of data but disappears when more data is added, it was likely a fluctuation. Persistent signals that grow with more data and are confirmed by independent experiments are credible. This multi-pronged validation has saved physics from numerous false discoveries. Historical examples illustrate the process. In 2011, experiments reported faster-than-light neutrinos. If confirmed, it would have upended relativity. The result received global attention. Further investigation revealed a loose fiber optic cable causing timing errors. The anomaly disappeared. This is science self-correcting. Initial errors are identified and corrected through scrutiny. In 2015, a diphoton excess appeared in LHC data at around 750 billion electron volts. Both Atlas and CMS saw it, though with modest significance. Theorists published hundreds of papers speculating on what new particle could be responsible. More data in 2016 showed the excess was a statistical fluctuation. It vanished. No new particle. This is normal. Fluctuations happen. The community investigates, adds data, and moves on. The Higgs discovery in 2012 followed the opposite trajectory. Initial hints in 2011 grew stronger with more data. Both ATLAS and CMS saw a resonance at 125 billion electron volts. The significance reached 5 sigma. Properties matched standard model Higgs predictions. Independent confirmation came from precise measurements. This is what a discovery looks like. It does not fade. It strengthens. So where does the crack in reality narrative gain traction if missing energy is well understood? The answer lies in how anomalies are reported and interpreted. Lepton flavor universality provides a case study. The principle states that the electromagnetic and weak forces couple with equal strength to electrons, muons and taus, differing only by mass. This is a cornerstone of the Standard Model. If violated, it would indicate new physics, possibly new particles preferentially coupling to certain leptons. LHCb measures rare decays of B mesons. These decays involve bottom quarks transitioning to strange quarks via the weak force. The rate at which B mesons decay to final states containing electrons should equal the rate for muons, accounting for mass differences. Early LHCb measurements suggested a discrepancy. The ratio of muon to electron decays was lower than predicted. This persisted across multiple decay channels and datasets. By 2017, the combined significance approached 4 sigma. This sparked intense theoretical interest. Could this be evidence of a leptoquark, a hypothetical particle coupling differently to different lepton generations, or a new Z-prime boson with flavor-violating couplings? Hundreds of papers explored possibilities. Experimental collaborations worldwide designed searches to test these models. Then came refined measurements. LHCb applied improved analysis techniques. They increased the dataset using run-to data. They reduced systematic uncertainties. In 2025, they released the full analysis. The result, no deviation from standard model predictions. The earlier tension disappeared. Lepton flavor universality holds. Why did the anomaly fade? Several factors. Early measurements had larger uncertainties, allowing room for fluctuations. Subtle systematic effects in particle identification and trigger efficiencies were better understood with more data. The improved analysis corrected biases that affected earlier results. This is textbook science. An intriguing hint drives refinement. Improved methods resolve the tension. The lesson is clear. Anomalies below 5 sigma are provisional. They guide research but do not overturn established theories. Many such anomalies populate the literature. Some grow into discoveries. Most fade. The process is iterative and self-correcting. Sensational headlines during the provisional phase mislead. They treat hints as confirmations. When the anomaly resolves, the headlines disappear. The public is left with the impression that physics is unstable or contradictory, when in fact the system is working as designed. How does this connect to the crack in reality narrative? Because anomalies, when first reported, generate excitement. Researchers speak cautiously about implications if the effect is real. The media strips away the conditionals. Theorists propose exotic explanations. These proposals are speculative, contingent on the anomaly being real. They are not claims that physics is broken, yet headlines present them as such. The cycle repeats. Anomaly reported. Speculation follows. Headlines exaggerate. Public perceives crisis. More data resolves anomaly. Correction receives minimal coverage. Cycle begins anew with the next anomaly. This creates a narrative of physics in constant turmoil, always on the verge of revolution. The reality is incremental progress punctuated by occasional breakthroughs. What should the public take away? Preliminary results are not final. Statistical significance matters. Replication by independent experiments is essential. Peer-reviewed publication is standard. Speculation is not confirmation. These principles apply to all science, not just particle physics. Now consider the panic myths in detail. Each deserves thorough examination because they illustrate how scientific concepts are distorted. Micro black holes. The scenario is that LHC collisions produce black holes that do not evaporate. These black holes fall to Earth's center, accreting matter, growing until Earth is consumed. This fear appeared in lawsuits and media coverage. Understanding why it is unfounded requires examining both theory and observational constraints. General relativity, the theory of gravity formulated by Einstein, describes black holes. A black hole forms when matter is compressed within its Schwarzschild radius. For the Sun, this radius is about 3 kilometers. For Earth, less than 1 centimeter. To form a black hole, you must compress the object within that radius. At the scales and energies of the LHC, gravity is far too weak to create such compression. Based on standard general relativity, micro-black hole production is impossible. However, some theories propose extra-spatial dimensions. If space has more than 3 dimensions, gravity could become stronger at short distances. In these models, the fundamental Planck scale, where gravity becomes strong, could be as low as a few trillion electron volts. If so, the LHC could produce micro-black holes. Proponents of these theories emphasize that such black holes would evaporate instantly via Hawking radiation. Hawking radiation arises from quantum effects near the event horizon. Virtual particle pairs form near the horizon. One particle falls in, the other escapes. The escaping particle carries away energy, causing the black hole to lose mass. The evaporation rate is inversely proportional to the black hole's mass. Larger black holes evaporate slowly. Stellar mass black holes take longer than the age of the universe. Micro black holes evaporate in less than 10 to the minus 27 seconds. A micro black hole produced at the LHC would have a mass of a few protons, about 10 billion electron volts. It would decay into quarks, leptons, and bosons in an unimaginably short time. The detector would see a burst of particles. This would be a spectacular signature, easily identified. No such events have been observed. This absence sets limits on extra-dimensional models. But what if Hawking radiation is wrong? What if micro black holes are stable? This is the doomsday scenario. Here, cosmic rays provide the definitive safety argument. Cosmic rays with energies up to 10 to the 20 electron volts strike Earth regularly. That is 1,000,000 times higher than the LHC. Over billions of years, Earth has been hit by more cosmic ray collisions at LHC equivalent energies than millions of LHC experiments could produce. If stable micro black holes could be created at these energies, cosmic rays would have produced them. Some would have stopped in Earth, the Moon, or other astronomical bodies. If they accreted matter, effects would be observable. Earth's core would show anomalies. Neutron stars would degrade. White dwarfs would collapse. None of these effects are observed. Astronomical bodies remain stable. This proves that even if micro black holes were stable, they do not accrete matter dangerously. The argument is even stronger for neutron stars. These are remnants of supernova explosions, composed almost entirely of neutrons. They have masses about 1.4 times the Sun compressed into a sphere 20 kilometers in diameter. Densities exceed 100 trillion times that of water. Cosmic rays striking neutron stars produce collisions in their interior. If stable, accreting micro-black holes formed, they would sink to the core and begin consuming the star. Over millions of years, the star would degrade detectably. Observations of neutron stars show no such degradation. They behave exactly as predicted by known physics. Pulsars, rotating neutron stars emitting radio beams, maintain precise timing. X-ray binaries, where neutron stars accrete matter from companion stars, exhibit predicted behavior. This constrains the properties of any hypothetical stable micro-black holes. Even if they exist, their accretion rate must be negligible, rendering them harmless. The LHC Safety Assessment Group quantified these arguments. They calculated the number of cosmic ray collisions equivalent to LHC collisions that have occurred in astronomical bodies. For Earth, the number is over 10 to the 22 in the past 4.5 billion years. For neutron stars, even more. If dangerous black holes could form, we would see evidence. We do not. This is a robust, quantitative safety argument. Strangelets. The strangelet scenario involves hypothetical stable lumps of strange quark matter. Ordinary atomic nuclei contain up and down quarks. Strange quarks are heavier and appear in short-lived particles like kaons. Some theories propose that a configuration of roughly equal numbers of up, down, and strange quarks could be stable and lower in energy than ordinary matter. If true, a strangelet touching ordinary matter could catalyze conversion. Protons and neutrons in atomic nuclei would rearrange into strange matter, releasing energy and propagating the conversion. The process would spread exponentially, converting Earth into a dense, dead lump. This is the ICE-9 scenario. Why is this extremely unlikely? First, theoretical models of quark matter do not support strangelet stability under realistic conditions. Quarks interact via the strong force described by quantum chromodynamics. QCD calculations suggest that strange matter is only stable, if at all, at very low temperatures and high baryon densities. LHC collisions create extremely high temperatures, over 10 trillion degrees Kelvin. This is far too hot for strange matter condensation. Think of it this way. Strange matter forming at LHC temperatures is like ice forming in a blast furnace. Thermodynamics forbids it. The second law dictates that systems evolve toward higher entropy. A low-temperature condensate cannot form in a high-temperature environment. The energy released in the collision rapidly thermalizes, creating a hot quark-gluon plasma. As this plasma expands and cools, it hadronizes into ordinary particles. There is no pathway to strangelet formation. Experimental evidence from the relativistic heavy ion collider supports this. RHIC collided gold nuclei at energies lower than the LHC, creating conditions arguably more favorable for strangelet production. Extensive searches found no strangelets. Upper limits on production rates are well below any level of concern. The LHC, operating at higher energies and thus higher temperatures, is even less likely to produce strangelets. Additionally, strangelets, if they existed, would likely be positively charged. Ordinary atomic nuclei are positively charged. Like charges repel. A positively charged strangelet approaching a nucleus would be repelled by electrostatic repulsion. It would not touch the nucleus. No conversion would occur. Even negatively charged or neutral strangelets would interact weakly with ordinary matter, given the rarity of close nuclear collisions. Cosmic rays again provide a benchmark. High-energy cosmic rays collide with the lunar surface, producing conditions similar to heavy ion collisions. The moon is composed of ordinary matter and has been bombarded for billions of years. If strangelets formed and converted matter, the moon would show signs. It does not. This observation, combined with RHIC and LHC data, rules out dangerous strangelet production. The LHC Safety Assessment Group reviewed strangelet scenarios thoroughly. Their conclusion? Strangelet production at the LHC is either impossible or so rare and harmless that it presents no risk. This conclusion rests on both theoretical understanding and experimental limits. Vacuum decay. This scenario is more subtle and requires careful explanation. The concept arises from quantum field theory. Fields like the electromagnetic field or Higgs field have potential energy curves. The lowest point on the curve is the true vacuum. If the universe currently resides in a local minimum, not the global minimum, it is in a false vacuum. A quantum fluctuation could create a bubble of true vacuum. The bubble would expand at the speed of light, converting false vacuum to true vacuum. Inside the bubble, physical laws would differ. Particles might have different masses. Forces might have different strengths. Structures like atoms, molecules, stars, and galaxies would disintegrate. This is vacuum decay, a phase transition of space-time itself. Some calculations based on the measured Higgs boson mass of 125 billion electron volts and the top quark mass of 173 billion electron volts suggest the standard model vacuum is metastable, not immediately unstable, but vulnerable to tunneling into a lower energy state over timescales vastly longer than the age of the universe. The concern is whether LHC collisions could trigger this transition prematurely. Why are collider energies not comparable to cosmic scales? Vacuum decay requires sustained high energy density over macroscopic regions. LHC collisions involve enormous energy density, true, but confined to a volume smaller than a proton and lasting less than 10 to the minus 23 seconds. This is insufficient to nucleate a vacuum bubble. Calculations show that the probability of triggering vacuum decay in an LHC collision is absurdly small, far below any conceivable concern. Cosmic rays achieve higher energies and interact throughout the universe. If particle collisions could trigger vacuum decay, cosmic rays would have done so. The fact that the observable universe remains in its current vacuum state, despite countless high-energy collisions over billions of years, proves that such collisions do not catalyze vacuum decay. The LHC operates within the safety envelope established by nature. Furthermore, the metastability timescale, if the vacuum is indeed metastable, is estimated at 10 to the 100th power years or longer. This dwarfs the age of the universe, 13.8 billion years. Vacuum decay is a cosmological issue, not a laboratory concern. It might occur spontaneously far in the future, independent of human activity. It is not something particle colliders can influence. The LHC Safety Assessment Group addressed vacuum decay explicitly. They noted that theoretical uncertainties in the calculations are large. The vacuum might be fully stable. If metastable, the decay timescale far exceeds any human relevance. And even if it were less stable than calculated, particle collisions do not provide the conditions to trigger it. The conclusion: no risk from LHC operations. These three scenarios, micro black holes, strangelets, and vacuum decay, share common features. They are speculative, based on extensions of known physics. They are constrained by cosmic ray observations. They have been reviewed by independent experts and found not to present risks. Yet they persist in popular imagination because they sound dramatic. A black hole consuming Earth, matter converting to strange matter, the universe phase transitioning out of existence. These are vivid, terrifying images. Scientists address these fears through patient explanation and quantitative arguments. The cosmic ray analogy is powerful because it is empirical. Nature has conducted the experiment. Results are clear. No danger. This should be reassuring, yet skepticism lingers. Why? Partly because the scenarios tap into deep anxieties about technology and unintended consequences. Partly because the reassurances require understanding physics most people have not studied. This is where communication becomes critical. Physicists must explain not just that the LHC is safe, but why in terms accessible to non-specialists. Analogies help. Comparisons to cosmic rays ground the argument in observable reality. Transparency about safety studies builds trust. Publishing detailed reports, allowing independent review, and engaging with public concerns demonstrates responsibility. The LHC Safety Assessment Group's reports are public. They are detailed, technical, and thorough. They address every hypothetical risk raised. They show the calculations. They cite observational evidence. They conclude, based on rigorous analysis, that LHC collisions are safe. This level of transparency is rare in high-stakes technology. It should be applauded. Yet the panic myths persist. Why? Because sensational claims spread faster than careful rebuttals. A headline screaming, "LHC could destroy Earth," gets more clicks than LSAG report confirms LHC safety. Social media algorithms amplify outrage and fear. Nuanced explanation requires time and attention. Sensationalism offers immediate emotional gratification. This brings us to the distortion chain. How do legitimate scientific results become sensational headlines? The process involves multiple steps, each adding distortion. Step 1. A research group observes something interesting. They measure a quantity that deviates from predictions. The deviation is small, perhaps 2 sigma. They write a paper describing the measurement, uncertainties, possible systematic effects, and the need for more data. The language is cautious. Words like suggests, may indicate, requires further investigation appear throughout. The paper is submitted to a journal or posted to the Arkhivchev preprint server. Step 2. The collaboration decides to highlight the result in a press release. Press offices aim to make research accessible and interesting. They consult with the researchers, then craft a narrative emphasizing the novelty and potential significance. The press release might say, "New measurements hint at possible deviations from standard model predictions, though more data is needed to confirm." This is accurate but opens the door to interpretation. Step 3. Journalists receive the press release. Science journalists with expertise in particle physics read the actual paper, interview the researchers, and write balanced articles. They explain the measurement, its context, the statistical significance, and the caveats. The headline might read, LHCb Experiment Reports. Tension in leptin universality measurements. This is responsible reporting. Step 4. The article is shared online. Social media users write their own headlines or captions. A tweet might say, CERN scientists discover particles behaving unexpectedly, possibly breaking fundamental laws of physics. The link is to the balanced article, but most people only read the tweet. The distortion begins. Step 5. News aggregators and less specialized outlets pick up the story. They rely on the press release or other articles, not the original paper. They prioritize clicks. A headline evolves into CERN experiment challenges. Physics could rewrite understanding of universe. This is further from the source and more sensational. Step 6. YouTube channels, bloggers, and social media influencers create content based on these secondary sources. They add speculation, dramatic visuals, ominous music. A video titled CERN Just Broke Reality. Scientists panic as particles defy physics garners millions of views. The original cautious measurement is now unrecognizable. Step 7. The story spreads. Comments, shares, and reactions amplify it. Algorithms prioritize engagement, which favors sensational content. Corrections or rebuttals from scientists get buried. The narrative takes on a life of its own, disconnected from the original research. Months later, when more data resolves the anomaly and the researchers publish updated results showing no deviation, the follow-up receives minimal attention. The initial sensational story lingers in the collective memory. This asymmetry biases public perception. People remember the drama, not the resolution. Teaching viewers to recognize this pattern is essential. When you see a headline about CERN breaking physics or discovering alternate dimensions, pause, ask, is there a link to a paper? What collaboration is involved? What is the statistical significance? Has the result been replicated? Are scientists using cautious or absolute language? If the answers are unclear, the claim is likely exaggerated. Look for red flags. No named experiment, no paper, absolutist wording, claims of cover-up or suppression. These indicate unreliability. Conversely, green flags include named collaborations, links to peer-reviewed journals or archive, cautious verbs, statistical significance stated, acknowledgement of uncertainties. These indicate credibility. Apply this to the crack in reality narrative. If the claim is that CERN discovered a crack in reality, ask for specifics. What experiment? What was measured? What does crack in reality mean physically? If the claim cannot be traced to a specific verifiable measurement, it is almost certainly false. Legitimate physics results are specific. They report measured quantities, uncertainties, and interpretations. An example, the ATLAS collaboration measures the Higgs boson mass to be 125.09 plus or minus 0.24 billion electron volts. This is precise, testable, and published in peer-reviewed journals. A claim like CERN discovers portal to another dimension lacks specificity. What was measured? What is a portal? How does it relate to known physics? Without answers, the claim is meaningless. The crack in reality narrative likely originated from a combination of missing energy searches and resolved anomalies, distorted through the chain described above. Missing energy searches are real. They constrain dark matter models. But they have not found evidence of new particles escaping into other dimensions. Anomalies like the leptin universality tensions were real, but they resolved with more data. Neither justifies the crack in reality framing. What would a true breakthrough look like? Consider the Higgs discovery. Both ATLAS and CMS independently observed a new particle. The significance exceeded 5 sigma. The particle's properties match standard model Higgs predictions: spin zero, even parity, decays to pairs of photons, Z bosons, W bosons, bottom quarks, tau leptons. The results were published in high-impact journals. Independent confirmation came from detailed studies. This is a discovery. Or consider gravitational waves. LIGO detected signals from merging black holes in 2015. The signal matched general relativity predictions for the waveform. Independent analysis by multiple teams confirmed it. Follow-up observations by additional detectors validated the detection. Astronomy entered a new era. This is a breakthrough. A crack in reality would require similar rigor. A measurement showing clear, reproducible violation of conservation laws with 5 sigma significance. Confirmation by multiple independent experiments. Theoretical explanation that integrates with existing physics or compellingly argues for revision. Peer-reviewed publication and scrutiny. Sustained signal with more data. None of this exists for crack in reality claims. So, the real crack, the boundary of our models, is where the action is. The standard model is incomplete. We know it. Dark matter exists but is not in the standard model. Dark energy drives cosmic acceleration but has no standard model candidate. Neutrino masses require physics beyond the minimal standard model. Matter-antimatter asymmetry is unexplained. Gravity is not quantized. These gaps are not failures, they are opportunities. Each unsolved problem points toward new physics. The LHC probes these frontiers. Every measurement that confirms the standard model narrows the space for new theories. Every search that finds nothing rules out models. This is progress. It tells us what new physics is not, guiding where to look next. The Higgs discovery completed the standard model but also raised questions. Why is the Higgs mass 125 billion electron volts? Naive calculations suggest it should be much higher, requiring fine-tuning. This is the hierarchy problem. Supersymmetry, a proposed extension of the standard model, could solve it by introducing partner particles that cancel problematic contributions. But LHC searches have not found supersymmetric particles. This constrains or rules out many supersymmetric models. Extra dimensions could also address the hierarchy problem. If gravity spreads into extra dimensions, it would appear weaker in our 3 spatial dimensions. The fundamental Planck scale could be much lower than the standard 10 to the 19 billion electron volts. The LHC has searched for signatures of extra dimensions like Kaluza-Klein particles or missing energy from graviton production. No evidence found. This constrains extra-dimensional models. Dark matter searches continue. If dark matter consists of WIMPs with masses accessible to the LHC, they should be produced in collisions. Missing energy signatures would reveal them. So far, no convincing signal. This pushes WIMP masses higher or their interactions weaker. Combined with direct detection experiments, which search for dark matter scattering off nuclei, and indirect detection, which looks for dark matter annihilation signals in cosmic rays, the allowed parameter space shrinks. Eventually, either dark matter will be found or the WIMP paradigm will be abandoned in favor of alternative models. Precision Higgs measurements test the standard model at high precision. The Higgs couples to particles proportionally to their mass. Deviations from this pattern could indicate new physics. Measurements of Higgs decays to bottom quarks, tau leptons, W bosons, Z bosons, and photons all confirm standard model predictions within current precision. As more data accumulates, precision improves. Tiny deviations, if they exist, will become visible. The Higgs self-coupling is particularly interesting. The Higgs field has a potential that includes a term proportional to the Higgs field to the 4th power. This determines the Higgs self-interaction. Measuring the rate of Higgs pair production constrains this coupling. Deviations could hint at new physics modifying the Higgs potential. Current measurements are consistent with predictions, but uncertainties are large. Future runs and future colliders will improve this. Rare decays probe new physics indirectly. Many processes forbidden or highly suppressed in the standard model could be enhanced by new particles in loop diagrams. Measuring these decays with high-precision tests for virtual effects of heavy, undiscovered particles. The Higgs decay to muon pairs recently observed is an example. The branching ratio matches predictions, constraining models that predict enhancements. CP violation, the difference in behavior between matter and antimatter, is another frontier. The standard model includes CP violation, but not enough to explain why the universe contains matter and virtually no antimatter. Additional sources of CP violation must exist. Searches in B Meson decays, charm decays, and other processes look for deviations from standard model predictions. Some tensions have been observed but not at discovery level. This remains an active area. Neutrino physics intersects with collider physics. The LHC can produce tau neutrinos, which are harder to study in other experiments. Detectors like FACER and SND at LHC, located along the beamline, detect neutrinos produced in LHC collisions. This provides complementary information to neutrino oscillation experiments and could reveal properties like sterile neutrinos or new neutrino interactions. Each of these research directions represents the real crack, the boundary where known physics meets the unknown. Progress is incremental, but it accumulates. Each measurement refines our understanding. Each null result constrains theories. This is not the dramatic narrative of a crack in reality. It is the patient, systematic exploration of nature's laws. What measurement would settle the biggest uncertainty next? For dark matter, a combination of LHC searches, direct detection, and indirect detection will either discover it or constrain it to very specific scenarios. If WIMPs exist in an accessible mass range, one of these methods should find them within the next decade. If not, alternative dark matter candidates like axions or sterile neutrinos will take precedence. For the Higgs mechanism, precise measurements of Higgs properties will determine whether it is truly the standard model Higgs or has modifications hinting at new physics. The high luminosity LHC, scheduled to begin in 2029, will collect 10 times more data, enabling percent-level precision on many Higgs couplings. Deviations, if they exist, will appear. For neutrinos, determining the mass ordering, measuring the absolute mass scale, and discovering whether neutrinos are Majorana or Dirac particles will require dedicated neutrino experiments. These include long baseline oscillation experiments, neutrinoless double beta decay searches, and cosmological observations. Together, they will constrain neutrino properties tightly. For matter-antimatter asymmetry, precision measurements of CP violation in B, CHARM, and other systems will either discover new sources or push the scale of new physics higher. Kaon decays, studied at facilities like NA62, also contribute. The combination of collider and fixed target experiments will narrow the possibilities. For quantum gravity, the LHC will not directly probe Planck scale physics, but indirect effects like modifications to scattering amplitudes or production of Planck scale relics are possible. Null results constrain quantum gravity models. Future colliders, like a 100 trillion electron volt machine, might access scales where quantum gravitational effects become significant. The future of particle physics involves both energy and precision frontiers. Higher energy colliders can produce heavier particles directly. Higher precision measurements can detect virtual effects of those particles. Both are necessary. The LHC provides both, and its successors will continue this dual approach. Beyond colliders, astrophysical observations offer complementary insights. Gravitational wave detectors probe strong field gravity, testing general relativity in regimes inaccessible to colliders. Cosmic microwave background measurements constrain early universe physics, including inflation and primordial density fluctuations. Large-scale structure surveys map dark matter distribution, informing models of what dark matter could be. Particle physics, cosmology, and astrophysics are converging. Questions about the early universe, dark matter, and fundamental forces are interconnected. Answering them requires collaboration across disciplines. The LHC is one tool in a larger scientific enterprise. Its results inform and are informed by other experiments. This integrated approach maximizes our chances of breakthroughs. The crack in reality narrative misses this context. It treats physics as fragmented, unstable, on the verge of collapse. The reality is coherence. The standard model works extraordinarily well. Extensions and modifications are explored systematically. Progress is measured and cumulative. The public deserves to understand this, not as a feel-good story, but as an accurate description of how science operates. Scientists have a responsibility to communicate clearly, to explain not just results, but the process, to convey uncertainty without sounding uncertain, to acknowledge gaps without implying ignorance. This is challenging. It requires skill, patience, and willingness to engage with non-experts on their terms. Many physicists do this well. Organizations like CERN invest in public outreach, education, and transparency. But sensationalism has structural advantages. It is simpler, it grabs attention, it fits into existing narratives of crisis and revelation. Countering it requires sustained effort, not just one-time corrections. It requires building scientific literacy so that audiences can evaluate claims themselves. It requires media that values accuracy over clicks. These are societal challenges, not just scientific ones. The crack in reality narrative will persist as long as incentives favor sensationalism. But individuals can resist by asking for evidence, by tracing claims to sources, by understanding the difference between observation and interpretation, by recognizing red flags and green flags, by demanding rigor. These habits of thought generalize beyond physics to all areas where expertise and evidence matter. The LHC's legacy is not a crack in reality. It is a vast data set, billions of measurements, thousands of papers, incremental progress toward understanding nature's deepest laws. It is the training of thousands of young scientists who will carry this work forward. It is technological innovations, from superconducting magnets to distributed computing, that benefit society broadly. It is the demonstration that international collaboration on grand challenges is possible. And it is the affirmation that human curiosity, rigorously applied, can unveil secrets of the universe, not through dramatic revelations, but through patient inquiry, not by breaking physics, but by refining it, not by finding cracks, but by mapping the boundaries of the known and venturing cautiously into the unknown. That is the story, not panic, not crisis, progress.